Thanks, Amaury, for the introduction, and thanks everybody for coming. So indeed, I'm on sabbatical at the University of Paraná in Curitiba, and so it's a great pleasure to come to USP. As I learned today, I should pronounce it, and I'll tell you at the end why, because there's a strategic partnership between Princeton and USP that maybe allows us to do some more exchanges in the future. So today the topic that Amaury suggested I focus on is on large eddy simulation of scalar exchanges, and by scalar probably everybody understands, but just in case, scalar means temperature and relative humidity or CO2 or things that are not basically the velocity vector in this case. And so I'm going to talk mostly about the physical and computational challenges and what we need to overcome them. This is mostly the work of Chili, who used to be my PhD student. The second part is the work of my ex-PhD student, Hamid Reza Omidvaran, in collaboration with a number of people inside and outside of Princeton. So the big challenge is that we want to design better cities in the 21st century. This is Shanghai in the 80s, and this is Shanghai today. The level, the speed of urbanization in China has just been staggering. But in other places, Sao Paulo or New York, or in many places, when these places were urbanized, it was a little bit like that. So very rapid urbanization, and this will continue because of the economic incentives for people to migrate to cities. They remain very strong, and so the estimate is that the urban population will keep growing while the rural population will flatten out. And basically by 1950, we expect about 70% of the people to live in cities. And that 70% is also equivalent to a 70% increase in the number of people living in urban area compared to 2014. Now, we're going to have 70% increase in the number of people living in cities between 2014 and 2050. But the density of these population and these cities are not constant. In fact, if you look at the whole world, the average density of cities is declining because we live in bigger apartments, because we want more parks. So it's declining by about 1% per year. And this is very different between different cities. But this is the average over the world from this book. This is Manhattan in 1910. And this is Manhattan today. If you think New York is crowded, it used to be much more crowded in 1910. The height of the bar is the average density of the population. So if you combine the 70% increase in people with the 1% decrease in density, that will give you this blue scenario, which again, according to this book, is going to give us a doubling of the urban land use by 2050. So the number of buildings and streets and highways that we have will basically double. So it basically means that 50% of the buildings and infrastructure that we will use in 2050 have not yet been built, which could be, a scary prospect. But it could be also an opportunity to design and plan these buildings and infrastructure better than what we have done in the past to maintain better environmental quality and sustainability in cities. So with this urban expansion come also a range of other stressors. So population growth and expansion is one stressor, but we also, when we think about the cities of the future, we think about climate change, how technology can transform cities, environmental quality, natural disasters, and aging infrastructure. And so the urban future will shape the mitigation of and the vulnerability and adaptation to these other shocks. And so the basic idea is we want to design cities that are more sustainable, more livable, and more resilient. So how do we do that? Of course, I'm not going to talk about health and transportation. I'm going to focus on the aspects that are related to climate. And so when we think about urban climate, we try to represent cities in weather, climate, or Earth system models as some sort of a special surface that basically has buildings, there's radiative trapping inside the canyon, and that exchanges momentum, heat, humidity, and CO2 between the roof and the atmosphere, between the walls and the canyon, between the ground and the canyon, between the canyon and the atmosphere. And we represent them using these kind of resistances. And these resistances are representing the surface exchanges that basically are occurring across the solid-fluid interface. Now, the problem that we faced when we started looking at this is that some of these formulations of the resistances date from some work done in 1924 in a wind tunnel in Germany by a scientist called Jürges. So, and you can find that you can trace back some of the models that we use today to this paper, which was over a flat wall. So these really are outdated. The representation of these resistances is really outdated, so we want to improve it. And the questions to improve it that we start with is, what are the transport processes that these resistances are kind of encoding or parameterizing, and how to parameterize them better? And also, how different are the transport processes for scalars, such as temperature and water vapor, compared to momentum that's associated with the velocity? Okay? So now, so again, what we are interested in is the exchange of scalars and momentum between the surface and the atmosphere. Now, if instead of a city we had ice or salt flats, we would be in a situation where the roughness elements, the sand grains in a salt flat, or the undulations of the ice would be very small, less than a few millimeters. So these roughness elements are embedded in what we call the viscous sublayer of the flow, which is the layer where basically viscous forces dominate over inertial forces, and the Reynolds number is very low. This is what would be what we would call a smooth wall. And over a smooth wall, you have the viscous sublayer, few millimeter, buffer layer, few centimeter, and then you have your typical log layer, where you have a log law that applies, that we are basically familiar with, except that the Z0 for a smooth wall is basically related to the viscosity of the fluid. Now, we know in most environmental applications, Z0 is not dependent on the viscosity, because these are basically, well, let me finish by saying something about smooth wall. In smooth wall, the shape of the roughness is not important. What is important is only the molecular processes that occur in this molecular viscous sublayer. So the viscosity and and viscous diffusivity control both the drag, which is the exchange of momentum, and the exchange of scalars such as heat or evaporation. Now, in most environmental application, these roughness elements are very high. They protrude into the roughness sublayer. They could be a few meters or more than a few centimeters. This could be grass, this could be rock, this could be cornfields, or so on. In this case, the dynamics are somewhat different. We still have a log layer here, but as we typically know, the Z0 here depends on the roughness. It depends on the roughness because for rough walls, where these roughness elements are too high, the shape of the roughness is indeed very important, because now the drag, the momentum exchange, is no longer related to viscosity. It's related to the pressure or form drag that the flow interaction with these roughness elements creates. So now the shape of the roughness is important. It controls drag and the velocity field. However, there is no pressure for scalar exchanges. I'll come back to this point. And so molecular processes continue to control scalar exchange, just as we had in a smooth wall. So for a rough wall, there's more difference between momentum and scalar exchange. And this is a rough wall. Now, what the urban areas canonically are rough walls, but we turn them as very rough walls. Why do we add this very? The very is to say that the roughness protrudes well beyond the viscous sublayer. So these are really, really deep. And also because we are not only interested in the average flow above the roughness elements, we are also very interested in the flow in between the roughness elements. So I don't care what happens between two corn plants or between two grass leaves, but I care about what happens between two buildings. So by very rough, we mean these are very rough, and we also want to predict the flow in between the building. This is the campus of the Swiss Federal Institute of Technology, and this is some LES simulations that we've done basically of this flow. You see all the flow structures, and you see how if you go a little bit further, the flow blends out. So let's go back to this physical origin of the difference. So if you think about the exchange of momentum or the drag on the flow, that basically you need to predict the velocity field, u, v, and w. When you start going to a very high Reynolds number in a rough wall case, the flow impinges on this cube. There's the flow is brought to zero velocity. By Bernoulli equation, you get very high pressure. And the pressure here is larger than the pressure here. And you create what we call the pressure drag on this cube. Now, and to represent this in Reynolds average Navier-Stokes simulation or large eddy simulation, you need a good solver for the pressure, and you need to represent your cubes and the force they exert on the flow well. Now, on the side, you still have here a region where the viscosity, which is related to the flow parallel to the surface, is going to be important. And for these viscous friction effects, they are not related to the pressure field. The colors here are the pressure. This is not working very well, but keep trying. So here you basically still have some viscous drag, and you need, because the pressure disturbance is large, it is resolved in the CFD, while the viscous sublayer is very thin, so typically a few millimeters. We don't resolve it, and then we need a wall model, as I'll come back and explain it. So the question is, what is the role of the Reynolds number? The Reynolds number measures the effect of inertia, which causes the pressure drag, to viscosity, which measures the viscous drag. So if you have a very high Reynolds number flow, this is going to be very important, and this is going to be negligible. If this is negligible, it means viscosity is no longer important, and so it doesn't matter how high you make your Reynolds number, things are going to become Reynolds number independent. So we know that this happens. If you, for example, measure the drag coefficient, which is basically the drag force normalized by this quantity, for a flat plate, actually you realize that after a Reynolds number of 10 to the 4, the drag coefficient becomes constant. It means it doesn't matter if you keep increasing the Reynolds number and making the inertial forces larger. The viscous forces are already negligible, and the inertial forces dominate, and so you can make the Reynolds number infinity. It all is the same. This is dominated by inertial forces. Viscosity has no role. And then you get this kind of flat plate constant CD. So for a non-streamlined bluff shape like a flat plate, the pressure drag dominates at very high Reynolds number. So in the cities, we are in this region. And in Rance LES, wall modeling is not going to be important, because wall modeling tries to tell us about viscous drag. Viscous drag is negligible. We don't care about it. And so this makes basically simulating flow over cities, believe it or not, a somewhat of an easier problem, right? Because if the CD is Reynolds number independent, it means you can put a cube in your wind tunnel at this value, at 10 to the 4, measure the CD, and the CD would be applicable to a city. So you can do low Reynolds number simulation and measurements and apply them to the real cities. This is what I mean by it could be an easier problem. It's not that easy, but it's easier. Now, the problem is buildings are not flat plates. Buildings have round roofs and other kind of complex geometries. And you see, when you go to more complex geometry, the CD is no longer exactly constant. It starts dipping here. This is what we call the drag crisis, related to the separation of the boundary layer. So sometimes viscosity sneaks back in to become important at high Reynolds number, because it could control the very thin boundary layer around the object. So round objects, for example, round roofs are more tricky. So this is a video in a wind tunnel. It starts with a flat roof. You see the circulation over a flat roof. This is round roofs, and before that it was angled roof. You see that basically, let me rewind it. You see that the flow here is pretty much, the vortex is trapped between the flat roofs. Here there's a very different type of circulation, and here is also very different when you go to round roofs. So the street ventilation is very different. So even though we said the flow is simpler to predict, it's not that simple, especially when you go to complex geometries. For example, when we try to validate simulations with using Fluent in large eddy simulation mode, for a flat roof, you see that, let's compare black to black. The black line is Fluent. The black dots are the observations from a wind tunnel. The match was pretty good for a flat plate. For a round roof, the match was much less satisfactory, because basically when you have complex round geometries, simulating those round geometries are more complex. But despite this complexity, I would argue that basically simulating the flow is the easier problem compared to simulating heat transfer or evaporation. Why is that so? Well, in the heat transfer equation, unlike the Navier-Stokes equation, there is no pressure term. And so there is no pressure drag or pressure heat exchange. There's no heat exchange that's modulated or done by the pressure. So all the heat exchange has to happen by viscous or molecular means, which means that basically the flow parallel to the surface, or basically the details of the viscous sublayer that controls this exchange, is going to be very important. And so now our model is not resolving anything. Now we need to parameterize this viscous sublayer using what we call a wall model, and that becomes a much more complicated problem. So already the simulation is more complex. What adds to the complexity is that these problems never become Reynolds number independent. And physically, because viscosity is always acting as the process through which heat is transferred at the wall, viscosity is always important, and so the Reynolds number, which measures inertia to viscosity, is always important. So I showed you that CD becomes independent of the Reynolds number for drag. The equivalent for heat transfer is what we call the Stanton number, is Nusselt divided by Reynolds times Prandtl. So this would be, Stanton would be Reynolds number independent for, let's say, a constant fluid, only if the Nusselt number goes like Reynolds number to the power 1. Now, the problem is that the Nusselt number does not go like Reynolds to the power 1. In fact, any experiment will show you that Nusselt is going to go like Reynolds to some m, which is less than 1. So here, the slope of this is Nusselt divided by Reynolds, so on a log-log plot. So the slope is this m. You see that the slope is not 1, but not only that, the slope changes. So for low Reynolds number, you have a smaller slope. For high Reynolds number, you have a higher slope. So basically, you cannot do some measurements at low Reynolds number and translate them to higher Reynolds number. So basically, the problem of heat remains Reynolds number dependent. And that means if you want to measure heat transfer from a real building or from a city, you need to match the real world Reynolds number. So you cannot do a wind tunnel experiment or a direct numerical simulation and translate it to the real world. The physical reason is that there's no pressure drag, and scalar transfer must occur through viscous exchanges. If viscosity is important, the Reynolds number is always important. And basically, again, the dependence of molecular diffusivity becomes important. So, of course, getting the momentum and velocity right is a prerequisite to getting the heat flux right. But the heat flux is a much harder problem because it's always Reynolds number dependent, and because you need to get the transfer in the very thin viscous sublayer around every window and every roof and every wall correct. So how do we study this heat transfer problem? Usually, we can do wind tunnel studies or direct numerical simulations, which are the solutions of the full equations, but which are limited to low Reynolds number by computing. Or we can do something called wall-resolved LES, which is basically you do LES, but near the wall you refine the grid to the point of resolving the viscous sublayer, which becomes very, very expensive for high Reynolds number. So for these techniques, we're limited to low Reynolds number, which basically means that we have limited Reynolds number range, orders of magnitude lower than the real world. So you cannot extend your findings from the experiments that you've done to the real world, given the Reynolds number disparity. Now, advantages are, of course, these are techniques where no parameterizations or wall models needed, and you can vary the setup very easily in DNS or in wind tunnels. Otherwise, we can do real-world measurements, which are always extremely useful. They give us ambient conditions. They are at the real Reynolds number of the real-world problem, these are kind of good attributes. The shortcomings is often we have only one-point measurements. If you measure the exchange coefficients here, you can measure the middle of the tunnel, the middle of the roof is different from the end of the roof. And sometimes they can be difficult to generalize because of the fine details for example, the measurement location specificity. If you measure over one roof, is it applicable to another roof or so on? So what we want to hopefully do is wall modeled LES. And by wall modeled LES, I mean we're going to do LES, but without trying to resolve the very thin viscous sublayer around every wall. The idea is that a wall modeled LES can inform us on what happens again right above and also in between the roughness elements. Now, the idea of LES is that you have, let's say, the largest turbulent eddy that you're trying to resolve, which is, let's say, on the order of the height of the ABL. This is the smallest scale of the eddy. This is the Kolmogorov length scale. And typically, if you do direct numerical simulation, you resolve all the scales. So you have the domain is that large and the grid cell is that small. Now, this, again, large Reynolds number, the two are very distant, and you would need a ridiculous number of grid points. We cannot afford it. So LES, the idea is you resolve the large scales that you think are more important, and you try to model the results, the small scales. And again, if we do wall modeled LES, we just kind of keep our delta in the inertial range. We don't try to go into the dissipation range. This is what wall modeled LES means. But that means that if you basically near the wall, where if your viscous sublayer is important, your viscous sublayer is here, and you need to model these small dissipation range scale in the viscous sublayer, you need to model them, and this is why this is basically the flow near the wall is modeled. Now, alternatively, you can do a wall resolved LES where you near the wall you bring the delta all the way here, but again, this becomes very expensive. So we want to do LES, and so wall modeled LES is a useful tool because it allows us to do a large Reynolds number that's comparable to the real world. It's computationally affordable. We can do complex geometries and apply it to heat transfer. Some hurdles, the classic challenges of wall modeling in LES. We need the wall model to tell us what's happening in the viscous sublayer. For vertical walls, we need to modify the log law because Monin-Obukov is for horizontal wall, not for vertical wall. And we have the challenges of representing buildings in the domain. So in our LES, we represent the building using something called the immersed boundary method. So we keep the grid as is, but if there's a building, we add a pseudo force in that grid cell to represent the effect of the building. It's an old method. It works pretty well now. It's widely used. We use pseudo-spectral methods to compute derivatives in the horizontal direction, and we use this subgrid scale model. In fact, I'm going to skip over some of these next two slides. It's not important. All I want to say here is that if you do this, you get some numerical problems that you need to resolve, and we resolve them, we get this better. So not very important, not very critical. Now, remember that we need a wall model, and so even though the city is rough, if you think about each roof or each wall, these are like smooth surfaces. So for each roof or each wall to model the flow really above the wall or next to the roof, we're going to use an equilibrium wall model based on Kader and Yaglom that basically relates the velocity just very close to the roof to the roughness of the roof facet itself. This is again an equilibrium model for each facet, not for the whole city. Same thing for the scalars, and we're going to do this dynamically, updating U star depending on if we get fast or slow wind. So again, I'm going to actually probably skip this too. Well, okay, let me think about it. Okay, so we have this wall model. Let me actually do this because this might be interesting for other applications. So we have a wall model. Now, Monin-Obukov similarity, it's a correction of the log law for when you have buoyancy. And so if buoyancy is going to generate turbulence in the vertical direction, And by generating turbulence in the vertical direction, it increases basically the vertical fluxes in the ABL. And so we use this Monin-Obukov correction basically to correct for this extra turbulence. Now, if you have a vertical wall, if you have a building wall that's vertical, buoyancy still acts in the vertical direction because that's the direction of gravity. So now buoyancy could generate turbulence, but that turbulence is parallel to the wall. So this turbulence cannot make the exchanges between the wall and the fluid stronger because this is in the wrong direction. They're not parallel to the wall. So I had some colleagues in Australia. They did some DNS of the vertical wall. And the result that we basically got is that if you have a vertical wall and you want to write a log law for wind or temperature, you should completely get rid of the Monin-Obukov correction. So this behaves very much like a neutral flow, and you should not include the Monin-Obukov similarity correction in your wall model for vertical walls. So we did all that in the LES, and we first started now comparing to wind tunnel and observations. So the first thing we did is compare to wind tunnel from Nakamura. They had an internally heated copper cube placed in a low-speed wind tunnel. It was near neutral, so the temperature was like a passive scalar. And we did a large eddy simulation of this case, but at a larger Reynolds number, more of a real-world Reynolds number than what they did. So it was much higher than their experiments. Now, one thing we need to be able to predict is, again, I told you that Nusselt goes like Reynolds to the M. M is very important to predict because M tells you about the efficiency of heat exchange between the wall and the wall and the fluid. So if you rewrite this, you can say that you can show that if you plot it on a log-log scale, M is the slope of the log of Nusselt versus log of Reynolds. So M is typically what these studies try to predict. So this is the M from the LES for the front of the building, the side of the building, the rear, the top, and average over the whole cube. And we get values between 0.9 and 0.89. And you see that the experimental values are much lower. So there's clearly a discrepancy. And that leaves us asking, what is the problem here? Is it our LES, or is it that Nakamura's Reynolds number is very, very small? So we notice quickly that this is basically the 0.5 is almost close to the laminar limit, which is telling us that maybe the Reynolds number is so small that the inflow is almost laminar. So to address this question, we now compare to the same, this M, but now instead of a wind tunnel, we go for a real-world building. In this study, Aya Hagishima measured this M over 4 locations over a roof. So now the Reynolds number is exactly similar or comparable to our LES. And now where we compare the M, actually, we get a much better match. So the results of Aya Hagishima gives us an M of 0.89, but also if we see other real-world measurements, the average M is somewhere between 0.89, 0.85, or something much higher. And the LES now does a much better job in capturing these real-world or these field-observed M, and both are much, much higher than the wind tunnel. So what that tells us is the wind tunnel is underestimating M, underestimating the efficiency of heat exchange between a building-like cube and the real world. So this gives us a lot of confidence in the LES that we're not completely obscene in thinking that LES can actually be a reasonable tool for predicting heat flux. It seems that the efficiency is very much related or comparable to the real world. Again, all these are values of M. So LES and field values of M are very close, much higher than wind tunnel. And what that tells us is that even if your LES is not perfect, doing it at the right Reynolds number gives you smaller error than doing wind tunnel or DNS at a wrong Reynolds number. So now we have an LES tool that we trust. We continue to validate it and do other kind of tests, but we think that our LES code is now in a reasonable shape. And now we can start asking questions such as how are momentum and passive scalar transport differently over high roughness surfaces. So to do that, we did a flow over a bunch of cubes. And again, you have the classic frontal area and planar area index. And now in LES, you can vary them. And I will not explain these because probably the crowd here is familiar with that. And so what we did is we basically, we did a cube, but then we did 8 other cases where we maintained lambda p constant and we varied lambda frontal. So we made them from very wide to very slender cube. This is a top view. And now we are trying to ask the question, basically, we go back to this question, what are the processes that these resistances are basically trying to parameterize? So the first thing you want to do is compute the turbulent fluxes, obviously. This is an XZ slice through the domain of the instantaneous U and W. So the U and W are given by these streamline arrow. And the color is the scalar concentration. And in a flow that varies in space, you cannot use spatial averaging to define a Reynolds number. And so your turbulent flux is the correlation of the temporal correlation of the local instantaneous quantity. So you measure at one single point, you measure a time series of W and T, and the temporal correlation of W and T is your turbulent flux. That's, for example, what an eddy covariance measurements in a city will be estimating. And if you're far above, then you basically your turbulent fluxes are homogeneous, and if you measure with an eddy covariance, here you're measuring the correct average fluxes. Now, however, when you get really close to the buildings, you get something called the dispersive fluxes. What are the dispersive fluxes? So in a flow that varies spatially, the net average vertical flux is actually is W times T, averaged in time and then averaged in space. This is kind of this is what the Reynolds average is. And you can divide this into your classic eddy covariances or your classic temporal correlation eddy covariance. But you also have this term, which is the mean, the time average W multiplied by the time average T and then averaged in space. Now, typically, over a flat terrain, we know that W bar is 0. We actually rotate, we were just talking about that, we rotate the flow so that the average W is 0, and so this term is 0. And so the total advective fluxes are only kind of the eddy covariance, and you measure this, and you get the total fluxes. And so again, this bar is kind of the bar is averaging in time, which is equivalent to Reynolds average, and the bracket is averaging in space. Now, so again, for a smooth wall or far from the roughness, if you're at twice the height of the buildings, W is equal to 0, and your eddy covariance gives you the correct fluxes. However, if you're doing LES and you're interested more in the region near the building, in this region, the average W is not 0. For example, here you see circulations where obviously W is very large, and you cannot assume that the W is 0. So this term is not 0, and this term is what's typically in complex flows we call the dispersive fluxes. So the dispersive fluxes are the spatial correlation of the temporally average quantity. What does that mean? It means that basically the flow here is always going down, and the flow here is always going up. And if basically you have, if the time averaged flow has some spatial correlations, then that will result in dispersive fluxes. For example, this structure will always take maybe, let's say, temperature and sweep it up and cause these dispersive fluxes. So you need to account for them. So you need to account for these fluxes. Now the question is, how important are these fluxes compared to the turbulent fluxes? Well, they're not important if you're at 2 times the building height, but when you start getting into, this is the height divided by the building height, so this is elevation normalized by building height, so the building roof is here. So if you're in the first 2, if you're within to building heights, these dispersive fluxes are going to be very important. The dispersive fluxes are the solid line. The dashed lines are the turbulent fluxes, both normalized by the sum, by the total fluxes. And again, the different colors are the different canopies. And you see again that when you get to the roughness sublayer, the dispersive fluxes can sometimes be larger than the turbulent fluxes, and you need to account for them. For momentum, but also for scalar, the same idea is that within the roughness sublayer, dispersive fluxes are very important and they need to be accounted for. Now, so then these resistances are not only trying to represent turbulent, but also are trying to represent some dispersive fluxes. So we kind of answered the first question, that both turbulent and dispersive fluxes are important. The second question we had is how are momentum and heat fluxes similar or different? We did a quadrant analysis, and if you don't know what quadrant analysis is, don't worry about it. So we have ejection, sweep, inner and outward interaction. The bottom line is this is the quadrant analysis for momentum, u prime and w prime. And this is for heat, w prime and theta prime. And what you see is that the lines here are very similar to the lines here, and so are the lines here at different points. What this tells me is that the quadrant analysis for momentum is very similar to the quadrant analysis of heat, which tells me that because the quadrant analysis is analysis of turbulent fluxes, it basically tells me that the turbulent transport of passive scalar and momentum are very similar, because when you try to do the quadrant analysis, you get the same answer about how important are ejections, how important are sweeps, etc., and these are at two different points. So so the dissimilarity between scalars and momentum is not coming from turbulent transport, it's actually coming from dispersive transport. Why is that? So this is kind of the dispersive perturbations, and this is again for momentum, and this is for scalars. So let's look at the momentum first. So you have a slow parcel. So the lines are the flow direction, and the color is the dispersive perturbation of u. So blue means basically the flow is slow, and red means the flow is fast. So here the flow is slow and going upward. So you have flow going upward, but with very little, with a negative u. So flow going upward with a negative u double prime. So basically slow flow going upwards, which basically tells you that the correlation between u and w is negative, which means you have a downward transport of momentum. Sorry, this is not, I should have rehearsed this explanation. It's not very trivial. But basically, you have slow flow going upwards, and it goes back here. And here, even before the flow accelerates, but even before it touches the next building, which is here, it feels the pressure effect of this building and slow downs. And here what you have is a slow flow going downwards. So this gives you a positive correlation of u and w, which means that the downward transport of momentum here is compensated or partially cancelled by the upward transfer of momentum here. So for momentum, the dispersive transport cancel each other in this area and this area cancel each other, because the flow slows down even before it touches the building. Now for heat, it's a different story. The roof and the walls are hot. So here you have upward transport of hot fluid, so heat transport upwards. And then the flow goes down and it's cooled. And now the flow cannot basically heat up before it touches the building, because there's no pressure term to heat it. For the flow to heat up when it touches the next building, it has to actually touch the next building. And by the time it touches the next building, it actually doesn't have enough time to heat up. So it's swept cold. When it goes down, it's still cold. So this is upward transport of hot fluid, downward transport of cold fluid. And these two actually both give you net upward transport. So these are helping each other, and these are canceling each other, which basically tells you that now the dispersive transport of heat and momentum are very different. And again, this goes back to the effect of pressure. Pressure is the main reason why the dispersive transport are different. Now, all the models of these resistances are based on theories that are purely for turbulence. And both of them treat momentum and exchange, momentum and scalar very similarly. What we are starting to say is that basically, well, first you need to capture the Reynolds number correctly in simulation experiments. Wall modeling is very critical. What we're starting to say is dispersive fluxes are very important component of what these resistances are trying to do or trying to represent. And that basically the dispersive fluxes for scalars and momentum are very different, so they have to be modeled differently. So if you think about modeling a turbulent flux, you think about surface renewal theory or a K-closure, dispersive fluxes would be very different. So basically, we still have a gap in our understanding of what these resistances are supposed to do. And now we're starting to kind of bridge this gap, and hopefully from here, the next step that we're trying to do is try to come up with better resistance parameterization than what we have so far. So this is the first part. The second part, I'm not going to go through it in any detail, but so everything I said so far is kind of at the building scale. You can take the same LES and say what happens at the city scale. So at the city scale, if you have very strong wind and some small heating, you get a plume of heat and pollutants. If you have very weak wind and strong heating, you get strong urban heat island, and you get more of a bubble circulation regime. With the same LES code, we can set it up to study the transition from plume to bubbles. And so here you see, sorry, this is how the LES would model a plume. This is a bubble, and this is a transitional regime. And basically, we came up with a dimensional analysis, not going to go through the detail, that tell us, depending on U inflow, how fast is the flow coming onto the building, onto the city, compared to the heat flux of the rural area, the convective velocity scale of the rural area. So if you take this dimensionless parameter and plot it versus the heat flux from the urban area normalized by the heat flux from the rural area, you get a regime where the wind is very strong, so U inflow is very strong. You get pure plume. Here you get plume bubble, pure bubble, and in the middle you have a transition. I'm not going to go through this in detail. I'll be happy to send you the results. But I want to also end up with a minute to talk about the USP Princeton connection. So in Princeton, we're starting a big initiative called the Metropolis Project, where we are trying to kind of get people, people from different disciplines to think about the future of cities. How can we make them more sustainable, resilient, livable, and equitable? So again, we want to think about how innovations and sensors and models and artificial intelligence, machine learning, material, and all of that, how can that make cities more effective? And the reason this is pertinent is that a few years ago, I don't know if Mr. Grandino Rodas is still the proctor. Shirley Tillman is no longer the president of Princeton. Now we have a new president. But this is an agreement between Princeton and USP that was signed a few years ago. It provides funding for joint projects. So the USP team and the Princeton team will get funding. The grant submission deadline was March 15, but it happens every year. So if you have, no matter what your field is, you can if it's urban climatology or something else, I just want to encourage you to look at this. This is the link I can share with Amaury, and he can share with you on the details. So if you have topics that you think there are some Princeton collaborators you can work on with, I would encourage you to look at this opportunity, particularly related to cities, which is kind of a big thrust of Princeton. So with that, sorry, my slides were not designed for the right time, but I hope you got the gist of what we are trying to do. Thank you.
We have time for questions. No questions?
Just one curiosity. Your model is an open source model, or?
No, it's not, but we're happy to share it. I mean, we don't really kind of... So there's also some versions that are very related. So this started with the LES of NCAR, National Center for Atmospheric Research, and then just like evolution, it branched out into... So the version that I have is not open source, but we're happy to share it. But there are closely related versions that are on GitHub. And I'll be happy to tell you about these. I mean, our version, we didn't put it on GitHub because we're lazy. But we typically are happy to share it with... It takes some documentation. And, you know, it's I mean, with these are kind of house codes. They're not very cleanly written. And so I would like to be able to make sure that if we're passing it on to a research group, we can help them run it and understand understand it. Yeah, yeah, because it's not very well documented. Yeah. Yeah, 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 yeah.
One more question. Yeah, I have one question. Anybody has? Is your least large jet simulation model what's the coordinate system you use in order to
yeah, yeah.
to get a building geometry?
Yeah, yeah. So this is I went through it very quickly. So it's completely Cartesian. And so the way we represent buildings, so to represent topography, you have two ways. Either you make your grid turn around the mountain or the building. This is kind of the terrain following coordinates that WRF uses. In ours, it's different. So you know, imagine this is your building, and okay, and let's say that these are your grid cells, right? So if this grid cell is completely occupied by a solid, the velocity should be 0 inside the solid. So when you write the equation to basically solve to integrate the velocity forward in time, it's equal to some right-hand side, which has pressure and everything. And so the immersed boundary method is a trick whereby you add a force, the immersed boundary method force. So you calculate what is the force that will give me 0 velocity inside the solid, and then you add it. So you put a force in, so your code doesn't know there's a solid. All it knows is that you added a force in this grid cell that made the velocity 0. And so if you zero the velocity where the solid is, you basically represent how the solid is going to affect the fluid. Because if the velocity is 0, now there's a pressure force that this region of the flow is exerting on the fluid. So it's very common now in LES and other CFD techniques. It started with Peskin in the 80s, and now IBM is kind of very popular because it's nice. It's terrain following coordinates have their own, you know, issues, and this has its own issues. But it's kind of it's nice that you don't have to change your grid, your mesh every time you change the geometry. Yeah, yeah. So yeah.
Any more questions?
Then the heat fluxes are more complex because you need to add a term for heat here.
No, so heat. I mean, heat does not have. Yeah, so heat, so the way you do it for heat is that typically when you have, you know, when you're doing the IBM, you add all these forces, right? But then what happens at the boundaries? So then you create a layer of ghost cells or extra cells or something else, and so you create an extra mesh around the building. And for heat, you model the heat, you measure the temperature in the flow and the temperature of the surface, and you model the heat flux here using a wall model. So the wall model for heat and momentum is to basically compensate for these boundary issues that this represents the pressure drag, right? And so for the viscous drag and the viscous heat exchange, you need this wall model. And this is why I was saying, this I can do well. There's a, you know, this is much more tricky. This is trying to resolve, viscous sublayer results. And this is why wall modeling is more important for heat, because that's the main source of heat, and why it's more challenging. So yeah.
Okay. Thank you very much.
Thank you, everyone. Thanks.